When working with serial inputs, such as from a USB serial cable or wireless transmission, time progresses this direction, usually when we describe this. So we're going to receive a series of inputs from an input like X, and we're going to receive like 0, then a 0, then a 1, then a 1, then a 0, then a 1, then a 0, then a 1, and so on and so forth. And oftentimes what we're going to want to do when we receive serial transmissions is to detect certain input sequences to make sure, like to either identify an object, who is sending us a transmission, or to figure out, okay, hey, they wanted to send us this information. So let's suppose we want to create a sequence organizer that detects the sequence 0, 1, 0, and let's look at that happen. So if we have this X as our input, we're going to need a Z for our output that's going to say, I just saw the input sequence 0, 1, 0. So as you can see here, when I have the input sequence 0, 1, 0, my output Z is going to output a 1. And then also similarly, we can overlap these two, so I got 0, 1, 0, and now this is going to output a 1. Okay, so the process that we're going to use to solve this is first we're going to design our finite state machine. Then once we have our finite state machine, we're going to build our next state table, which is going to tell us what our current state is as an encoding, our input, and then figure out our next states and our outputs and the inputs to our flip-flops. Once we have that, we can solve for some Boolean expressions to control our flip-flops and our external outputs. And then once we have that, we can build our circuit, which is going to have some flip-flops and some combinational logic to control everything. So let's figure out how to begin and design our 0, 1, 0 sequence recognizer. To begin, we'll need a start state. And so that's our start state. And what we want to assume is that we haven't seen anything in our start state so far. So we're going to say seen nothing. And my output in this state is going to be 0 because I haven't seen any part of my sequence. I have not detected my sequence, so I'm going to output a 0 for Z. And so what we're going to have here is I'm just going to do a quick little key to tell me that that's my state. This is my output Z. And then I'm going to have state transitions that depend on X. If I see a 0, that's the first bit of my sequence. So I'm going to go to a new state called scene 0. And in this state, I have not seen my full sequence. I haven't seen 0, 1, 0. I've only seen a 0. So I'm going to output 0. If I saw a 1 as my first bit, that is not the first bit of my sequence. So we're going to stay in the same state. I haven't seen any part of my sequence. We have both state transitions we need for the first state, so let's go to the next state. When I am in state I have seen a 0, if I see another 0, let's say I saw 0, 0, I've still only seen the first bit of my input sequence, so that's going to be a 0. And if I see a 1, so I get a 0, 1, that means I will have seen the first two bits of my sequence, so I'll have seen 0, 1. And I have not seen my full desired sequence yet, so I'm still going to output a 0. And that was if I saw a 1. And now I have both state transitions for my scene 0 state. For my scene 0, 1 state, if I see a 0, I have now seen my full sequence, and I'll go to my scene 0, 1, 0 state, and I'll output a 1. And that was if I see a 0. And if I see a 1, so let's suppose I see the input sequence 0, 1, 1, this last one is not part of my sequence. It's not the beginning of a new sequence. It doesn't match the state 0 or the state 0, 1. So if I get two 1s in a row, I'm going to reset my state machine to go back to the beginning state with a 1. Oh, sorry, I drew that line wrong. We're going to go with that one. Alright, and now if I just received 0, 1, 0, and I receive another 0, so I got 0, 1, 0, 0, this new 0 is basically the start of another 0, 1, 0 sequence, or potentially could be. So he's going to hop back to here, and if I get another 1, so I get 0, 1, 0, 1, that's a 0, 1 in the last two bits, so this will simply go back to the 0, 1 state because that's what I've seen most recently. And that completes our state diagram, and we can show you a nice clean version of that if you would desire to see that. Okay, now, as we mentioned, we're going to, since we have 4 states, we have 1, 2, 3, 4 states, we're going to have log base 2 of 4 flip-flops, round up, which is equal to 2. So we're going to need to have 2 flip-flops, and we're going to assign one to be D0 and assign one to be D1. And what we want to do now is build these combinational logic blocks here to control these circuits. To do that, we're going to build our next state diagram, and the way I recommend doing it is one state at a time. So if we are in the A state and we receive a 0, we're going to go to the B state. If I'm in my A state and I get a 1, I'm going to stay in my A state, and this A state is my C in a 0 state, and my output will always be 0 in my A state. If I'm in my B state, which was my C in a 0 state, that will, if I get another 0, I'm going to stay in my B state. If I get a 1, I'm going to move to my C state, and my output will always be 0 in my B state. If I'm in the C state and I get a 0, I'm going to go on to the D state, which is my C my full sequence, so C is my scene 0, 1 state. And if I get a 1, I'm going to return back to my A state, and my output will always be 0. And then when I'm in the D state, which is my 0, 1, 0 state, or I've seen all of that, if I get a 0, I go back to my B state. And if I get a 1, I go to my C state, and the output of my D state will always be 1. Now that I have that initial diagram, let's clean it up, make it look pretty. And now the next phase is to replace our next state variables, or next state meanings, with some encodings. So what we're going to do is just replace A with 0, 0, B with 0, 1, C with 1, 0, and D with 1, 1. It's fairly arbitrary, but it works. And so we get, this was our A state, and this is our B state, for example. This is B, this means I'm going to C. This means I'm going to D, this means I'm returning to A. This means that I'm going to B, this means I'm going to C. So we just simply do a copy, cut and paste, and replace the letters with the state encodings. Now that we have our state encodings, we need to figure out how do we get these next states given our flip-flops. Since we're using D flip-flops, the inputs to our flip-flops, D1, D0, are going to exactly mirror our next state variables, because our next state for a D flip-flop is always equal to the D input. So what we can do is just simply replace the next state variables with our flip-flop inputs, and now we know what we want to input into our output and how we want to craft the inputs to our flip-flops. So we can derive some Boolean expressions, so we can see that Z is going to be equal to Q1, Q0, because just these guys down here. We can see that D0 is every other row, and it matches the complement of X, and then D1 is equal to, well, it's got 3 inputs, so it's got this guy and this guy are basically give us Q0X, and then we've got Q1, Q0 bar, X bar. So Q1, Q0 bar, X bar. And now we've got a set of Boolean expressions. From these Boolean expressions, we are going to create our circuit. And so we're going to create 3 circuits, one for CD1, and then one for CD0, and then one for our output Z. So we have D1, D1, or 0, 1, 0. And what we saw earlier was that D0 is equal to X prime. So we're just going to put that in there. And then D1, let's hop back, was Q0X. So we are going to put X and Q0 into an and then we had Q1, Q0 bar, X bar. So that's going to come up from here. We could do that if you want. And then We're going to OR these two together with an OR gate and input that into our flip-flop. And then X was Q1 and Q0, and it together, and that creates our circuit. And so again, just recapping what we did, we created a finite state diagram, created our next state table, derived some Boolean expressions, and then built our circuit.